is about harmonic motion. Now, if you've taken physics before or even pre-cal before, you've heard of these terms. If not, this is going to be different and new for you. But if you think about it, the physics of it, you understand just as a person who lives in real life. If you take a spring, and you pull the spring and let go, what happens? Goes back up, comes back down, goes back up, comes back down, kind of like a sine wave. In fact, it is exactly modeled by a sine wave. So what we're going to be able to do is take these simple harmonic motion questions and write equations for them using the things that we've learned about these graphs and these functions. Now, those of you who are actually big science people, I know that there's like friction and energy loss and all the things that actually happen in real life, but because this is simple harmonic motion, we're assuming that all of that is negligible, so this is happening in a vacuum, it's perfect, we're going to make it work. So, here we go. The position of a point oscillating about an equilibrium position at time t is modeled by either the position for time is a cosine of omega times t, or s of t equal to a sine of omega times t. So that weird looking W, remember, is omega. It is taking the place of the letter B that we had for all of our functions previously in this chapter. So because it's applying to something in real life, we're changing it to the letter omega. The amplitude of this motion is still a, whatever is in front of sine or cosine. The period is 2 pi divided by omega this time, since omega is in the place of b. The formula changes from a b to omega. And the frequency of this oscillation is omega over 2 pi. Now, a frequency in math and in science is how many times the shape has appeared in a specific amount of time. But what's easy to think about for frequency is that it is the reciprocal of period. So if you find the period of an oscillation, the period of a function, and then I ask you for the frequency, just flip a fraction over, and that's the frequency. One more thing we'll write down is because period is 2 pi divided by omega, it also leads us to know that the omega is equal to 2 pi divided by the period. Again, in the same way that b is 2 pi divided by period, omega acts as the same. We've just changed the letter because it's applying to something in real life. So let's see what this might look like. In example 1, we're going to suppose that an object is attached to a coiled spring, such as the one in the figure. It is pulled down a distance of 5 inches from its equilibrium position. Equilibrium means middle. And then released. The time for one complete oscillation is 4 seconds. We're going to give an equation that models the position of the time of the object at time t. So the two things I need for this is I need A and I need omega. So let's think about this. If we take this in real life, we take the spring here at equilibrium and we pull it down. How many inches did we pull it down? 5. So my amplitude, or the distance I've moved it, is 5 inches down. So I'm going to make the A equal to -5, again, because I've moved it down 5. So we've pulled it down 5, so it's starting below. We then go on to say that the time for one complete oscillation is 4 seconds. Well, that is the period of the oscillation, which means omega is going to be 2 pi divided by that number 4. And 2 pi divided by 4, if you reduce that fraction, the 2 and the 4 cancel each other out or reduce down. That's just pi over 2. So now we just need to put these two numbers, the A and the omega, in the correct formula. Our options are to use sine or to use cosine. So let's think about this in terms of what's happening. If this were a graph, and I took the spring and I pulled it down and started a stopwatch right when I let go, would I be modeling cosine or would I be modeling sine? It starts in the middle? I started my stopwatch when it was in the middle? I started it when it was at either a maximum or a minimum, which means it's going to be which one? Cosine. So when we write this function, we would write the position at time t would be equal to -5 times the cosine of pi over 2 times t. Because all I had to do was fill in a and omega and then decide if it was sine or cosine. Now again, because we pulled it down before we started, that's why it's cosine. If we said we just let it go from equilibrium, that would be sine. Because sine starts at a middle, cosine starts technically at a maximum, but because we've reflected it with that negative, it can start at a minimum. Now part B here says to determine the position at t equal to 1.5 seconds. So I've let go of it, I'm looking at my stopwatch, and at 1.5 seconds, I want to know its position. Well, t equals to 1.5 really just means that I want you to take 1.5 and I want you to plug it in for t, which means we are evaluating -5 times the cosine of pi over 2 times 1.5. That's just a calculator question. Now, I will warn you, my geometry classes have started using trig, but they're working only in degrees, and some of your calculators may have been switched to degree mode, so check real quick, make sure it's in radian mode since we're using radians in this class, and then evaluate -5 times the cosine of pi over 2 times 1.5. So we calculate, we'll round to 2 decimals here. So this should be approximately 3.54 inches. So now my question for you is, at the time 1.5, is this spring above the equilibrium point or below the equilibrium point? What makes you say below? That's a great idea. Our equilibrium point is at 0 though. So since we have a positive output, this is actually going to be above the equilibrium point. There will be times your function will give you negative distances, which just means that's below the equilibrium point. Part C here says to find the frequency. Now, frequency can be made really hard. If you look at a graph, you're counting how many times the wave shows up in a particular time, or you just think about the fact that it is the reciprocal of the period. So the period of this function, it says that it completes 1 oscillation in 4 seconds. So what does that mean our frequency is? What's the reciprocal of 4? 1/4. That's it. Our frequency is 1/4 oscillations per second. So if we were looking at our stopwatch, in 1 second, we've only completed 1/4 of a full shape.
Why do you use cosine?
Great question. So because in this question we pulled the function down, we're starting at a minimum. Sine starts at a middle, so cosine starts at the maximum or the minimum. Normally it starts at a maximum, but that's why we said negative, so that it can start at a minimum. Yeah, good question. So let's analyze some harmonic motion. It says that suppose an object oscillates according to the model S of t equal to 8 sine of 3t, where t is in seconds and S of t is in feet. Let's fill in the blank here. The motion is harmonic because the model is, and then we're just going to fill in those definitions. S of t equal to a sine of omega times t. If it fits one of those two descriptions, so a sine of omega t or a cosine of omega t, it is simple harmonic motion. What does a equal? Yes, but in this problem specifically it is 8. So since a is equal to 8, the object oscillates 8 feet in either direction from its starting point. What is the period of this function? Ooh, gotcha. The period, remember, is 2 pi divided by omega. So what's my period here? 2 pi over 3. Now, For help, this is 2 pi over 3, which is approximately 2.1, just so we can see both of those values. The period, which is approximately 2.1, is the time in seconds it takes for whatever this is modeling to complete one oscillation, one back and forth. The frequency is the reciprocal of the period, so the object completes 3 over 2 pi, flipping over that fraction, which is approximately 0.48 oscillations per second. So there's a lot of extra sciencey things that we can do with these harmonic motions. I just need us to be able to apply it to graphs, which means I'm going to ask you for amplitude, period, and frequency, and maybe midline if it moves up and down, but it probably won't. To apply this to a larger scientific idea, no longer talking about simple harmonic motion, but damped oscillatory motion, which is actually probably what happens more often in real life. So think about in real life, when you pull that string down and you let it go, yes, it goes up and down, but does it actually stay going up and down for forever? No, because we have things like friction and we have things like gravity working on our objects to reduce motion. So if we think about that, we can actually model those things with different types of functions. This is called damped oscillatory motion. So it's damped means like dampened or getting smaller. So like the spring in real life would bounce the highest points at first, and then it would get lower and lower and lower until it doesn't move anymore and it goes back to its equilibrium point. A decrease in amplitude of a damped oscillatory motion usually follows the pattern of exponential decay. And so what we're going to do is we're just going to explore what this looks like on a graph. I'm not going to have you really do anything with this besides just realize that it's pretty cool. So in example 3, a typical example of damped oscillatory motion is provided by the function s of x. I'm going to make this one blue. S of x equal to e to the negative x cosine of 2 pi x. So this is still damped oscillatory motion because we have an amplitude, which is just being changed by exponential decay. We do still have our omega, which is 2 pi. We changed to x instead of t so that our graphing calculators can graph it because they don't speak in t's, they speak in x's. What we're going to do is provide a graph showing a minimum y value of -1, a maximum y value of 1 for 3 functions happening at the same time. We're going to have the blue function from the question, the damped oscillatory motion. I'm going to make sure that one's in blue on mine. Along with 2 other graphs, which is exponential decay and a reflected exponential decay. And we're going to see this on our calculator between 0 and 3. So this is a calculator moment, which means I do have to go back to my desk to show you my calculator, so you can see what this looks like. Okay, on our calculators, we're going to do the following. We're going to type all 3 of those functions into y equals. So for me, the blue, I almost got the colors right. The blue one is going to be e to the negative x, e to the negative x, multiplied by cosine of 2 pi. Oh, I should close my parentheses. I gotta start over. I messed up. Eek. Okay, our second equation is the red one. So for me, I'm going to make that negative e to the negative x. I'm just trying to follow my color code from my paper. And then my green one, so I'm going down to y5 so that it's the right colors for me. You can do them in order, it doesn't matter. E to the negative x. I just wanted these specific colors. Now, before you press graph, we're going to adjust the window that we're looking at. Now, I think in one of the notes I had you adjust your window already so you could check your graphs. So to do this, you press the window button, which is up at the top. You might have ignored it for your entire life. But we're going to change this to looking between 0 and 3 That's the x values I care about between 0 and 3. And then having a y minimum of -1 and a y maximum of 1. So I've changed 4 things on this screen. X minimum is 0, the x maximum is 3, and then y minimum from -1, y maximum to 1. When you press graph, and I think I got my colors right on here, this is what you should see on your screen. Here's the damped motion surrounded by these 2 colors. Now, if you notice, this screen is essentially what I've given you on your notes to fill in. So I want you right now to do your best job getting this graph to show up on your notes. So I'm going to start with my green and my red equations and then bring my damped motion in. Not my best, but that'll do. So this is the picture that's on our calculators, hopefully. So what's happening here is that the blue graph is showing the spring moving. And this is what probably actually happens in real life because we're never operating without friction in real life. But that spring is going to bounce, but then it's not going to bounce as much each time after that and eventually goes back to rest at equilibrium. This is what actual harmonic motion would look like when it has forces acting on it. It's not simple harmonic motion. Now, because this is bounded by exponential decay, if we look at that e to the negative x and its reflection, it has basically bounded on bottom and top our motion. It never goes really outside. Can't tell by my graph because I didn't graph it perfectly. But so to describe the relationship among the 3 graphs in part A, the graph of y3, which is blue, just so we can know this, is bounded something to y1, which is my green one. So it is bounded above by that green graph because the green graph is always sitting on top of the blue one. And my blue graph is bounded below by the red graph. So these 2 exponential decay functions, which we did learn about last semester, control how much the motion is going to bounce back and forth. The main ideas I need you to take away, though, is about amplitude and period, which again is something that we've talked about for our other functions as well. So if we can look at an equation and fill out something like example 2, then we're actually doing okay. This example 3 is just because I think it's cool and curious and worth talking about just in general for science and for math things.